So we are studying Kelvin double bridge, and the introduction to this topic was as follows. If you want to measure a low value resistance using a Wheatstone bridge, these are the four arms of a Wheatstone bridge, and suppose this is a low value resistance that you want to measure, and when you connect it with leads, etc., there will be junction resistances which will come in series with the actual resistance, and that will cause wrong measurement. Not only this R, to measure R, we may also need another low value standard known resistance that will also have this junction resistance problem, and that may jeopardize our measurement completely. Today we shall solve this problem, but for that we will need the mathematics that we developed yesterday for this apparently peculiar bridge, which has not just four resistances but also some extra arms in the form of a delta here. And for this bridge, yesterday we saw, if we ensure that P by Q equal to A by B while we vary these resistances, then at balance the condition will be R by S is equal to P by Q is also equal to A by B, and the gamma, this resistance, will not come in the balance equation at all. Achha, now let me draw a Wheatstone bridge. Let me put the source here so that I have more space. Okay, here this resistance Rx is unknown, but we know this is a low value resistance. These resistances, call them P, Q and S, they are known and variable, but suppose S is also a low value resistance. P and Q, we will take them to be of medium value, because we will always try to avoid very low and very high value resistances as long as possible. Okay, achha. Now we have these junction resistance problems. Okay, so we will use a 4-terminal resistance box for this Rx. Rx is a low value resistance, so it should be a 4-terminal resistance, and let this be one terminal, another terminal. Here also I will have 2 terminals. Let me not connect it yet. Now we know that whenever we connect anything to any of these leads, there will be problematic resistances coming here. Okay, Acha. Now let me do this. Let me suppose I connect this here and this also here. Okay, and this comes to this terminal and this comes here. Now you see some of these lead resistances are not going to create any problem. For example, this and this, okay, these two you can think, okay, this is a part of the supply line, okay, or part of the battery resistance, and that is not a problem. I mean, the battery may also have some resistance and that never comes in the balance equation. So this resistance you can think as a part of the battery resistance. No problem. In the same way, these two resistances you can also again think as a part of this resistance. So they are not going to cause any problem when I make this, when I write the Wheatstone bridge balance equation. Next, this resistance and this resistance, these two are in series with P. So you can think that this is being added to P, but P is a relatively larger resistance compared to this junction resistance. So when you add a small error to a relatively large value, that is not going to give a large relative error or percentage error. So this is also not a problem. Okay. In the same way, this resistance and this resistance, so this you can think as a part of Q. Q is a larger resistance. If you add something small to a large quantity, not a big deal. Okay. Achha. But now I have to join this like this maybe. As soon as I do that, then this resistance, I mean this one and this one, they are going to create problem. Okay. I mean these two are the most problematic ones. I mean no escape, no easy escape from these two. Okay. This is fine, this is fine, these are fine, no problem. But what about this? Okay. So what we will do is this. Let this resistance be there, but now let me make some space. Now what I will do, I will connect two resistances here, call them A and B, variable and known standard resistances, and this way I will make a bridge. Okay. And now let me call these two problematic resistances together as gamma. Okay. And this resistance, this small one, is in series with A. I will choose A to be of medium value. So something small added to A is not going to cause a big problem. This is also of medium value. So this little resistance is also not a problem. Only these two, which I am calling as gamma together, may cause a problem. But now you see that this bridge is actually this bridge, or which is also here, which we call a Kelvin's double bridge. And for this bridge, yesterday we found the balance equation, which is here, P by Q equal to R, this is X, R by S, and this balance equation does not depend on gamma. Here is our gamma. So our balance equation is not going to depend on this resistance, this unknown spurious problematic resistances. So here, if we maintain A by B equal to, once again please, A by B equal to P by Q, then at balance P by Q equal to A by B will also be equal to R by S, and it is independent of gamma. So all problems are solved. Yes, now you say what you wanted to ask.
So, how did you consider A and B as medium?
Because they are in my hand. I mean, I will choose them to be of medium value. P, Q, A, B and S, these are standard resistances, variable resistances and known. So I will choose them. R is the only unknown one. Okay, and if and R is the unknown one, that is of low value, I have no control over that. But all these resistances I can choose. Even S I can choose. Maybe I don't need a low value S, I can do with a medium value S. Then no problem, fine. But I am assuming that, okay, to get it balanced, I may need one more extra low value resistance. But if it is not low value, if medium value can balance it, then no problem, fine. But otherwise, there is a solution. Yeah.
Sir, sir, means can you explain again how the lower left and lower right two junction resistances won't affect? Can
These
you please say
two.
that again?
These two.
Yes, sir.
Okay.
Yes, sir. These two and right one.
Okay. Achha, let me just name them. Then it will be easy. What's wrong? Just a second.
Sir, a dialog box has appeared.
Yeah. Okay, good. Now it's working. R1, R2, R3, R4, R5, R6, R7, R8. Now let me repeat. R1 and R8 can be thought of as a part of battery resistance. Okay. And in normal Wheatstone bridge principle, you think of normal Wheatstone bridge. Do I have it anywhere? No. But in normal Wheatstone bridge, if you find the balance equation, that does not depend on battery resistance at all. Okay, so these two you think as a part of battery resistance, no problem. Then R2, R3, R6 and R7. R2, R3, R6 and R7, they are in series with larger resistances. So not a big problem. Okay, some student is starting a parallel meeting. I don't know what to do. Okay, fine. Okay. Acha. And then so this is done. Only R4 and R5, R4 plus R5, they are together gamma, and that does not affect the balance equation. Okay, balance equation does not depend on this gamma when we derive this equation. Does
But sir,
not.
battery resistance won't be medium, right?
Which one?
So we are considering R1 and R2, R1 and R8 to be neglected because it is a part of battery resistance.
Yes.
But battery resistance would also be small, right?
Small, fine, no problem.
But sir, we just said that if the connection resistance is medium, then it is not a problem, but it is also small.
No. See, battery is completely safe. If we draw a Houston bridge, this battery can have a resistance. This meter can also have a resistance. Okay. Now, if you find the balance equation, how do you find the balance equation? You basically equate this potential to this potential and apply potential divider rule. Okay. So, okay, if I take, say, for example, this potential as reference 0, this potential as V, okay, whatever the V may be, I don't know the value, but suppose this is V, then this potential, call it VA and VB, then VA will be at balance, no current is flowing through the meter, so this current is 0, so apply potential divider rule, then VA will be, just follow this path, Q and P, this will be V by P plus Q multiplied by Q. Okay, V by P plus Q is this current and multiplied by Q is this potential, and VB is equal to V then divided by R plus S multiplied by S, and you equate these two at balance, so you will get this quantity equal to this quantity at balance. Okay, and so you have Q by P plus Q equal to S by R plus S. Okay, let me now take the reciprocals and subtract 1 minus 1 on this side, R plus S by S minus 1. This will give P by Q equal to R by S. This is the balance equation, and while deriving this, nowhere this resistance comes in the picture, neither this resistance, so they can be of any value, low, medium, high, unknown, whatever, so that does not change the balance equation at all.
Okay, sir.
So yeah, we are done with this. One thing that yes.
Sir, how are we writing P by Q is equals to R by S?
Here in this Houston bridge.
No, sir. The above result.
Here. Oh.
Then at balance, yeah.
Yeah. So this is what we derived yesterday.
Oh, okay.
Yeah. Okay. So do a star delta conversion and some component to dividend thing, and you'll get that. Okay, fine. Achha. Next, since we are actually talking about Wheatstone Bridge so much, so let's continue on Wheatstone Bridge. Before that, let me tell one thing. How measurement error gets accumulated. Okay. Suppose we have a piece of resistance, and you measure the current through it with an ammeter, and you measure the voltage across it with a voltmeter, and right now you ignore the fact that ammeter is not measuring actual current through the resistance, but it is measuring the sum of these two current. Okay, that we have already discussed. That issue is there. Okay, for now you can assume that this voltmeter has very high resistance, so that problem can be ignored, because we are going to focus on another problem. Okay, so there are so many problems, it's better to focus on one at a time. Okay, so right now you assume that the voltmeter is measuring this voltage across resistance, ammeter is also measuring the resistance through the current through the resistance. Okay. However, suppose this voltmeter is not perfect. It has some error, and suppose the specification says this is 1% accurate. Actually, what they mean, it is not 1% accurate, they actually mean it is 1% inaccurate, otherwise it is useless. So the specification says 1% accurate. So that means that if the true voltage is say 100 volt, then the voltmeter will give reading between 99 and 101 ohm with high probability. That is expected. Okay. In the same way, suppose this ammeter also says say 2% accurate. That means if 1 ampere current is flowing, reading will come with high probability between 0.98 and 1.02 ampere. Okay. So I am measuring the voltage with 1% inaccuracy and current with 2% inaccuracy. Now using these two, I can calculate the power being consumed. Okay, so power will be product of V into current. Okay. Now when we multiply these two quantities, since both these quantities can have small error in them, the power will also not be perfect. That can also have a small error. Now the question is, how much is the inaccuracy in power? Inaccuracy in power measurement is how much? Is it 1%? Is it 2%? Or something else? Okay. So let us see that. So power, suppose this voltage reading, suppose V is the, suppose let me say V is the true voltage, true value, and measured value is V plus or minus some delta V. This is measured. Okay, this is true value. In the same way, suppose I is the true current and measured current or ammeter reading is I plus minus some error. This is the measured value. Okay, so then delta V by V is the relative error in voltage measurement or per unit error in voltage measurement. In the same way, here delta I by I is the per unit or relative error in current measurement. Okay, so now my measured power will be the product of voltmeter reading and ammeter reading. Okay, and we will assume these errors are small, that is expected normally. So measured power will then be Vi plus delta Vi plus delta IV plus delta V delta I. Now, since delta V and delta I both are small quantities, this is a square of, product of two small quantities, so we can ignore it in comparison to other larger quantities for simplicity. Okay, this is true only if both these errors are small. I should have plus minus. Okay, because error can be more or less than, the measured value can be more or less than the true value. Okay, so then relative error in power measurement, that will be this quantity Vi plus minus delta Vi plus minus delta IV, this quantity minus true power, which is V into I, divided by the true power. Okay, then this comes out to be, these two you can cancel, and here you will get delta V, then I by Vi by V. Okay, and then plus minus, here also plus minus delta I by I, delta I by I. Okay, now this quantity is how much? As we have said, this is 1%, and the other quantity, this is 2%. Okay, so that means plus minus, this is 1% is 0.01, plus minus 0.02. Now we have a plus minus sign here and here. This error can be positive, this can be both of them can be positive together or negative together, or one positive one negative. But the worst case and most bad case is when both of them have same sign. Okay, then that is the maximum error we can have, maximum bounding relative error, that will be 3%. 3% relative error when you take both of them to be of same sign. We don't know what sign they will have, we don't know, but we at least know that this is the worst case scenario. Okay, so what do we see? When we take the product of two quantities like this, where and both the quantities are erroneous with some uncertainty error, then the uncertainty in the product will, relative uncertainty in the product will be the sum or addition of relative uncertainties in the individual quantities. That is what we have learned. Okay, next let me give you a homework. Suppose you want to measure the resistance as above. From here you can measure resistance as V by I. So this is now a ratio of two quantities, and both of them are erroneous. So estimated resistance or measured resistance, that will be something like V plus minus delta V by I plus minus delta I. Okay, and the true resistance is V by I. You find out what is the relative error in measured resistance. Okay, that is your homework. Let me tell you the answer. The answer is in ratio of two quantities. Okay, the relative error or per unit error, relative error gets added. Just like in the case of product. Okay, so both for product or ratio of two quantities, the relative error is added. We have proved this product. We have proved this for product of two quantities here, and your homework is to do this for the ratio. Same thing same process you need to apply. Okay. So let me pause for a minute maybe and see if you have any question.
Sir, in the Kelvin double bridge, we assumed A by B is equal to P by Q. Is it only for obtaining the ratio as Rx by S, or is there any other idea behind that assumption?
No, that is, I mean, if so when we do the experiment with this bridge, okay, I have said that we have to maintain this. Okay, so if you vary P or Q or A or B, vary all of them in such a way such that these two ratios are always equal. That we have to do. Why? Because if we maintain this, then in the balance equation we saw that the balance equation does not depend on gamma. Balance equation is P by Q equal to R by S, which is also equal to A by B. Okay, but if you do not maintain P by Q equal to A by B, you can still get a balance. Why not? I mean, you can still get a balance, but then that balance equation may depend on this resistance gamma, which we do not know. Okay,
Yes, sir.
so to get rid of this, we have done that. Okay, fine. Achha. So let me now come to Wheatstone Bridge. Now, I mean, the story that I am going to tell now, the moral of that will be, I mean, don't measure anything blindly. I mean, all measurements have a lot of issues associated to them. We will see some of them in the context of a simple Wheatstone bridge. Okay, so we know the balance equation P by Q equal to R by S, and if R is the unknown, from this we get R equal to P by Q times S. Now when we do this experiment in lab or anywhere, the known standard resistances that we are using, they are not perfect. They can also have some error. Okay, and the specification of these resistances will will mention that how inaccurate they are. Maybe they are, maybe say PQ, S, P, Q and S are all 1% accurate. I actually mean 1% inaccurate. Okay, and then therefore the value of resistance that we will estimate by obtaining balance or null, that cannot be also perfect, 100% perfect. That is not possible. So how much error can that have? Can we say, since all our resistances are 1% accurate, our uncertainty or error in measurement of Rx is also 1%? Is it so?
3%.
Excellent. Excellent.
No, sir.
Excellent, excellent. Thank you. So you see that we are using a formula where we have product of two quantities and ratio, and just now we have said that when we take product and ratio, relative error gets added. So error in relative error, I mean, not absolute error, relative error in R, that will be 1 plus 1 plus 1 equal to 3%. Okay, so you should be aware and careful of this fact. But also, is this the only source of error when we measure a resistance using Wheatstone bridge? Can there be other sources of error? Okay, so this is one thing. Next, another. Yes.
The detector pointing null point.
Yes, sir, the detector.
Yes, very good. I'll come to that. Anything else?
The contact resistances.
Contact resistances are of course issues, and if these are small value resistances, then they are serious issues. And then I will not use Wheatstone bridge. I will use Kelvin-Doppler bridge. Yes, that is also true. Okay. Another fact about this this meter sensitivity, etc. I will come to that very soon. But before that, another easy thing I will mention. Suppose this standard resistance S that you are using, suppose S can be changed in steps of 1 ohm. Okay, normally a variable, normally a standard resistance won't be like rheostat, because then you cannot get the value of this resistance. So you can only vary it in steps. There will be some like a knob or some something, leads, etc., which you can control in discrete steps. Suppose this can be varied in steps of 1 ohm. Then I can never say that my Rx has very infinite precision. Okay, so this is the resolution. Okay, this is the resolution of varying S. So now let me ask, what is the resolution? What is the resolution in measured R, measured Rx? How can we find that? Okay, so that, okay, again let us come back to this equation. Suppose at balance P is equal to 1 kilo ohm and Q is equal to say 100 ohm, okay, and say S is let me take S is 100 ohm. So what should be the value of R? So S is R is estimated to be 1K, right? Am I correct? P by
Yes,
Q
sir.
10, R by S 10. Yes, I am correct. Okay, but now,
Sir?
yes.
Sir? Sir, means resolution means you can say that na means it's kind of error, means the least amount of error that can take place in the measurement of S is 1 ohm.
Yes.
Kind of error we can say that.
Yes, absolutely. Absolutely. Now we want to estimate that what you are saying, I mean, least amount, I mean, least amount of, I mean, by which, I mean, beyond which you cannot say more precisely. Okay, so now you see R is equal to P by Q into S. Now P by Q is 1000 by 100, that is 10 into S. So this is 10 into S. Now you can change S in steps of 1 ohm, and the way you have obtained balance, then this factor can be changed in steps of 10 ohms. So this has a resolution of 10 ohm. Okay, so my resolution is my measurement is not more precise than 10 ohm in this case. Okay, so that is another factor. Achha. Next, let me come to the meter sensitivity issue. Okay, Achha. That issue which you have already pointed is like this. Suppose somehow by adjusting these resistances I have obtained the balance. Now let me check how good my balance is. Say I vary this resistance by a small amount, and let me see whether I am getting deflection, and if I vary it in the other way, if I increase, suppose it deflects towards the right, then if I decrease it slightly, suppose it deflects towards the left, then I will be certain about that, okay, I have got balance properly. Okay. However, it may happen that when I vary this resistance by a small amount, then there will be a small amount of current flowing through the meter, and the meter may not be sensitive enough to detect that amount of current. Okay, and then I may still get no deflection. Okay, suppose I got this balance with, say, this one resistance equal to 10 ohm, meter is showing no deflection, then I increase this resistance to 11 ohm, meter is still not showing any deflection because the current is very small, I bring it down to 9 ohm, still no deflection because current is again very small, then I don't know whether it is actually 10 ohm or it is 9 ohm or 11 ohm. Then also I am uncertain about that. Okay, so that is the issue. Now let us take an example and understand it in more detail. Sensitivity of Wheatstone bridge. Okay, suppose let me take a simple example. Suppose at balance P, Q, R, S, everything equal to 1 kilo ohm for simplicity. Next, also suppose the battery EMF is say 10 volt, and suppose the galvanometer resistance, meter resistance is Rm equal to also say 1 kilo ohm, and suppose the minimum detectable current, minimum division in your scale of the galvanometer, minimum division or detectable current is equal to say 1 microampere. Okay, so let us see then what will happen. This is 1 kilo ohm, 1 kilo ohm, 1 kilo ohm, 1 kilo ohm. Here a meter with 1 kilo ohm resistance, and battery okay with negligible resistance for simplicity. Okay. And now this is 10 volt. Okay, acha. Then I have got a balance like this, but I want to check, is this balance a very nice sensitive balance? What if I say change this resistance by a small amount delta R, so that will disturb the balance and that will cause some current to flow through the meter, but will that small current be detectable enough? Let me ask this question in the reverse way. What is the minimum value of delta R for which I will get a detectable current in the meter? So what is the minimum value of delta R to get a detectable current? Okay, or you can also ask this in a different way, that for some value of delta R, how much will be the current and how much will be the deflection. Okay, and that is also a measure of sensitivity, that is the amount of deflection divided by the change in delta R, that is also a measure of sensitivity. Okay, so here I am asking what is the minimum value of delta R to get detectable current, which is 1 microampere. Let us see that. Okay, solution. So let me take this point as reference, 0 volt. This point is then at 10 volt. Okay, Achha, then that means in the absence of the meter, let me call this point A and point B. Okay, so in the absence of the meter, then this potential VA, how much is that? 0, 10, midpoint, so 5 volt, no doubt. Achha. VB is how much? This potential 0, 10, but this is not the midpoint. Okay, so this will be my calculation would have been simpler actually if I had taken it the other way, 0 this side, 10 this side. I mean, you can do it for the other case also, but my calculation will be slightly simple. That's it. Okay, so then VA is still 5 volt. Now VB, that will be this potential 1000 ohm plus delta R divided by this plus this. So 2000 plus delta R multiplied by 10. Potential divider rule, simply. Okay. That means VB minus VB minus VA, that quantity will be this minus this, 10 into no, actually it would have been easier in the other case. I would have got rid of 1 delta R. Anyway, let me continue, no problem. Delta R by 2000 plus delta R minus 5. Okay, please check my calculation thoroughly, otherwise I will make mistake. So 10,000 plus delta R by 2000 plus delta R, 1000 into 10 minus 5. This is the voltage between these two terminals when the meter is not present. Okay, in the absence of the meter. So now what I am going to do, I am going to calculate the current that will flow through the meter using Thevenin theorem. And for that I will find a Thevenin equivalent circuit as seen from terminal A and B. Okay, so this quantity is the voltage between A and B in the absence of the meter. That means this is the open circuit voltage between A and B, or V Thevenin, or open circuit voltage between A and B. Now let me find R Thevenin, that is the resistance between A and B in the absence of the meter. Resistance between A and B in the absence of meter. Okay, so the meter is not there. Okay, so let me break it slightly. Okay, now from here to here, how much is the resistance? You see, from here I have and to find the resistance we have to replace this voltage source with internal resistance, that means short circuit in this case. Okay, so that means these two terminals are shorted. Okay, so there is a short circuit like this when we are calculating the open circuit resistance between A and B. Okay, if so, then from here to here what do I have? I have these two resistances in parallel, and then this is joined, connected, then these two resistances in parallel. Okay, so then that means this is equal to this 1 kilo ohm, 1 kilo ohm in parallel, 1000 parallel 1000 plus these two resistances in parallel, that is 1000 plus delta R in parallel with 1000. Allow me to do a little approximation, and this is 500 plus so 1000 plus a little number parallel 1000, that will also be 500. I'm ignoring this little delta R. Okay, please allow me this Please mute yourselves. Okay. Acha. You can do your calculation taking delta R also, and you will get very close result that I am going to get now. Okay. So this is approximately 1 kilo ohm. This is Thevenin resistance. Okay. So now when we connect this battery, I mean connect this galvanometer, how much current will flow through the galvanometer? Use Thevenin theorem. So galvanometer current Ig, that will be V Thevenin divided by R Thevenin plus R galvanometer, or I am using a different symbol, R meter. Okay, R meter. Here also then let me say R current meter, I meter. So that will be then V Thevenin is here, okay, 10,000 plus delta R by 2000 plus delta R minus 5 divided by, this is 1 kilo ohm, this is also 1 kilo ohm, so 2000, and we want this to be equal to the minimum detectable current of 1 microampere. We want. If so, then my question is, if this is what we want, then what is the value of delta R? That is what you have to find out. You can solve it yourself, time is up, so you can solve it yourself at home. If you have a class, feel free to drop out and let me just quickly solve it. This is the last thing I will do. Okay, so I have 10,000 plus 10 delta R, 10,000 plus 10 delta R minus 10,000 5 delta R divided by 2000 plus delta R, and then whole divided by 2000. Okay, this is equal to 1 micro, means 1 by 1 2 3 4 5 6. Okay, then this cancels, 3 zeros I will cancel. Okay, and then that implies 1000 into 10,000. 10 delta R, 5 delta R. So 5 delta R into 1000. So 5000 delta R, that will be equal to 2000 plus delta R, which means 5000 minus
So
no,
you mean into 2.
into 2. Thank you, thanks a lot. Okay, so that implies, approximately implies, okay, this 2 delta, you can 2 from 5000 doesn't matter, so 5000 delta R is same as 4000 0 0 0 0 0 0, so delta R is equal to 4 by 5, that means 0.8. That means in this way, if you change your delta R by 0.8 ohm, approximately 1 ohm, you will not be able to detect that change. So don't claim that your measurement is as precise as 0.5 ohm or so. That is impossible. Okay. Please check my calculations. I may have might have made any mistake. Okay, please check it. But the point is, this is another issue, and all these issues, sensitivity of meter, resolution, accuracy of these standard resistances, all of them are there and they are present all together, although for simplicity we have considered one issue at a time.